Welcome to today's webinar titled Simplify Your Metal Additive Manufacturing Workflow, presented by 3D Systems and hosted by 3D Metal Printing Magazine. My name is Lou Kren. I'm the Senior Editor for 3D Metal Printing, and I'm pleased to serve as your moderator. We have two speakers with us today. Maoz Barkai is the Product Manager of 3D Expert Software for 3D Systems. With more than 25 years of experience in the manufacturing industry, Maoz began his career designing parts and molds, and for more than 20 years has held R&D and marketing positions at companies specializing in CAD/CAM software. For the past 4 years, he has been product manager for 3D Expert, the all-in-one integrated additive manufacturing software offered by 3D Systems. Gil Epstein is a product marketing manager at 3D Systems, responsible for the company's 3D Expert software solution. He holds a Bachelor of Science degree in electronic engineering from the Israel Institute of Technology and has more than 25 years of experience with high-tech companies, holding a variety of R&D and marketing positions. So now, please welcome Gil.
Thank you, Lou, for the introduction. Hello, everyone, and thank you for joining us today. There are so many issues relevant for additive manufacturing, so it was really difficult, but we had to pick only a few for today's webinar. We'll start with a few words about why additive manufacturing is a revolution. We'll then explain what is the additive manufacturing gap and what does it take to get from a 3D CAD model to a ready-to-print model and then to an optimized model. We'll then move on to discuss the importance of efficient additive manufacturing workflow, and we'll show you some use cases and examples. And we'll end up with a demonstration of the additive manufacturing workflow using our 3D Expert software. So with no further delays, let's begin. So we got used to see this title, the Additive Manufacturing Revolution, but what really makes additive manufacturing a revolution? So additive manufacturing is a revolution not because it is faster or cheaper or more efficient manufacturing technology. In some cases it is, in some cases it does not. It is a revolution because it enables to produce geometries that could not be produced before using traditional techniques. So when looking at additive manufacturing, we should not look at it as a way to manufacturing the same part by replacing simply subtractive techniques with additive ones. Look at it as a way to explore opportunities that cannot be addressed by subtractive techniques. Look for savings that are not necessarily direct savings, like the cost to manufacturing the part itself. Look for savings that are derived from the enhanced functional properties that you gain through the new geometry. And AM is a revolution because we must change our design mindset. On one hand, there are new opportunities regarding what is possible and what is not. And on the other hand, there are new considerations you should take into account when you design or when you prepare to print. So no matter if we are looking to produce complex geometries with enhanced functional properties, lightweight part without compromising on strength, reduce the number of parts you need to assemble, or apply surface texture to deliver functional or aesthetic benefits. These are all examples of parts that cannot be produced using legacy techniques. Most important, supporting additive manufacturing is becoming a key element in your ability to be competitive in this market. I would like to stress one more time that the new geometries enabled by 3D printing and the enhanced functional properties they provide, like lightweight or part consolidation, are important not necessarily because of the direct saving, meaning lowering the manufacturing cost of the part. They are important because of the indirect savings that can range from fuel savings to patient quality of life, in the case of lightweight, for example, lower assembly cost and enhanced durability in case of part consolidation. Or for this example with one of our customers, Scarlett, when they are talking about 35 to 70% cycle time reduction or reduced cooling time from 35 to 7.5 seconds, they refer to savings achieved in the production workflow. Savings achieved because of the fast and more uniform cooling, which is the result of using conformal cooling channels in their production mold. The geometry of this conformal cooling channels can be created only through the use of 3D printing. Another use case will show us additional benefits that we can refer to them as byproducts of the main incentive to use additive manufacturing. Usually there is one main incentive to select 3D printing for a specific part, but once you get to the new geometry, it usually provides additional advantages. So for example, the purpose of these burners, they are used to pinch glass. So their purpose is to distribute flammable gases as uniformly as possible through the small nozzle holes. Now, to make sure the nozzle holes don't deform because of the high temperatures, the burner is cooled using an internal cooling system. Now, due to insufficient cooling accumulated over several months of non-stop operation, tube attachment failed on the sealing plugs, or drill cooling holes came off. So obviously fixing these issues required lengthy and costly repair actions, which basically stopped the production line. So to reduce the downtime, a new cooling system was required. So a new geometry was designed with conformal cooling channels that are less than 1 millimeter away from the burning gas. Now, the results were, first of all, we achieved the main incentive for the new design, which means the lifetime of the part was tripled. But by moving or shifting to the new geometry, we also save 50% on material, which also lowers the material heat that needs to be evacuated with each burning cycle. And reducing the complex assembly, which was used to be more than 20 parts, into one single part. So although the new burners are approximately 20% more expensive to produce, they're in fact 60% more affordable when considering their tripled lifetime achieved because of the design in one piece and the optimized cooling. So as we just saw, additive manufacturing enables a new world of design opportunity and design freedom. But it doesn't mean that there are no manufacturing considerations we should be aware of and that we should take into account when we design or when we prepare the model to print. If you simply take a 3D CAD model and send it to print, most chances are, especially if it's a metal print, that the result will not match your expectations. There is an inherent gap between a 3D CAD model and a ready-for-print model. Preparing the model for print with, for example, the proper orientation or support structures is essential to bridge this gap and to get to successful prints. So to bridge the additive manufacturing gap, you need to have the right tools. First, a tool set that will reflect the additive manufacturing considerations. And second, a tool set to address these considerations and to take them into account during the design and preparation process. And this is exactly where the additive manufacturing software comes into play. If we take a closer look at all the functions that the additive manufacturing software should address, we can divide them to three main groups. The first one is preparations. We can refer to all these functions as essential for successful prints. You simply cannot do without them. The second one is optimization. These are the functions that make the difference between an additive manufacturing ready model and an optimized model, a model that is getting the most out of the additive manufacturing capabilities. The third one is manufacturing. These are the functions related to the actual print and post-processing operations. It is a good opportunity to mention that the manufacturing workflow doesn't end with the printer. There is a set of post-processing actions that we need to perform before getting the final part. And we better take the post-processing considerations into account as we do our design to print. For example, taking into account the impact of the part orientation during the print on the surface quality, which might require additional extra work of polishing to get to the desired quality, or manual work to remove supports, or even leaving holes to be able to remove the powder from hollowed volumes. If you're only looking to build some prototypes and the only thing that matters to you is to get a successful print, you might be able to do with only the preparations functions. But for real production, when you're looking to get highest repeatable quality at the lowest possible cost and the benefit from the additive manufacturing design freedom, then the optimization and manufacturing functions comes into play. There are two main types of additive manufacturing software solutions. The first are the independent software solutions, meaning multiple and not related solutions, each focusing on one or more of the functions we have just mentioned. The second type are the all-in-one solutions, incorporating all the functions required during the additive manufacturing workflow. The differences between the two approaches are better illustrated and understood if we look at the workflow that you see in front of you. Independent solutions require back and forth iterative process between different solutions, different functions, while the all-in-one solution offers a one-stop shop, including all the functionalities required during the process. Well, some people would say that maybe it is better to select independent solutions, each specializing in a very specific function. But as we'll see in a second, there are quite a few drawbacks for this approach. The very basic drawback is that in many cases, each software is using a different environment, which means that when you move from one function to another, you also need to change formats and use file conversions. So there is also a good potential for errors that you will have to spend a lot of time to fix. CAD integrity, for example, is downgraded with the conversion of BREP to mesh when you move from one solution to another or from one function to another. Second is the slow and complex process that you need to go through in case that some design modifications are needed, you need to apply to the model, which is of course a very common scenario in development environment. In many cases, you simply need to start the entire process from scratch. And third is the lack of common environment, which makes it very difficult to link between simulation results, for example, to corrective actions to handle the issues that are predicted. Some of these drawbacks might exist also within an all-in-one solution, if it is only a combination of independent software solutions that are loosely tied together under some kind of a framework. A true solution that will solve this issue is not only an all-in-one solution, but also an integrated one with inherent interaction between the various functions and the unified and history-based parametric work environment. And once again, we are back to the difference between using additive manufacturing for rapid prototyping or for production. Delivering prototypes is all about speed. In manufacturing, it's different. It's about quality at the lowest possible cost. So if you are considering additive manufacturing for just prototyping, you might find it difficult to understand the difference between the different solutions. But once you get to production, the bottom line in your balance sheet will clearly tell you the difference. The integrated all-in-one solutions offer a streamlined process. CAD integrity is maintained as BREP is handled using its native form without conversion. Being history-based makes design modification very easy, as you do not lose all the work you have done so far, but all the actions are applied automatically to the modified model. And last is a single and unified work environment where build simulation is an integral part of the design environment, making it easy to correlate between simulation and analysis results and the corrective actions you need to take. And this is exactly what is offered by the 3D Expert software. So 3D Expert is an integrated all-in-one software solution from design to manufacturing. It is an integrated solution that provides inherent interaction between the various functions. All is done within familiar history-based parametric CAD environment, so changes at any stage do not require to start the process all over again. This is what we call a true streamlined process, from design to post-processing. It is relevant, of course, not only to 3D system printers, as the software is compatible with any printer. Before we move to see the software in action, I would like to stress one more time the importance of looking at the workflow as a whole. Now, I could have put here customers' quotes about how fast is our lattice performance or about the ability to easily set printing strategies using 3D zoning and so on. All are good, all are important, and all are true, of course. But instead, I would like to share with you quotes that refer to the increase in productivity related to the change in workflow, which is the most important impact of using 3D Expert. MTI, for example, reduced the file processing time by up to 75% and increased the productivity by up to 40%. Now, 3D Expert helps them to better utilize their facilities and their investments in additive manufacturing. I once saw a sign in one of our customers' facility next to the CNC machines saying, "When they don't turn, we don't earn." So this is exactly true also in the case of additive manufacturing facilities. Sharon Tuvia stressed the fact that they completely changed and streamlined the workflow and not only moved from using multiple software solutions to a single one. Scarlett are referring to taking their productivity to a new level thanks to the ability to have full control over the printing parameters. And last is 3D Pro Metal, and they remind us that you need to have the right expertise to address the entire workflow from design to post-processing. This is a great example of 3D Systems' unique positioning as we hold expertise in both additive and subtractive manufacturing techniques. Now, in order to better understand and experience what does it mean to work with an all-in-one integrated solution in a history-based environment or in a unified work environment, we would like to use this opportunity to show you 3D Expert in action. For that, I will hand it now to Maoz to walk you through the 3D Expert demonstration.
Hello, everyone. We will now go through the printing process from start to end and see a few of the features 3D Expert has to offer. We have very little time, so we will only take a quick peek at each subject. We will be happy to elaborate more after the webinar. We will start with printer and material selection. We will start a new project. We start with the last printer we've used, but we can select from a long list of predefined printers and materials. It doesn't have to be 3D Systems printer, as the system is printer agnostic. If a printer does not exist on the list, we can create a new printer and define all of its parameters. In this case, we will pick the DMP 500 machine because our part is quite big and we need a big printer for it. Our next step is to import the printed part and modify it if needed. In this case, we're bringing in a step file. 3D Expert can import CAD data as CAD data. It does not degrade it into mesh formats like STL or 3MF. This means it can work with history-based parametric features, which means easy editing and modifications. 3D Expert can work with all generic formats like STEP, IGEST, VDA, etc., as well as direct read from all major CAD vendors, including SolidWorks, CATIA, NX, Creo, and Inventor. It can also read in all major mesh formats, such as STL, 3MF, OBJ, and more. We will now make a small modification to the part. There are 3 holes here that require a thread, and we will want to add materials to allow for it. We will add a 2 mm offset to these holes. We can now examine the change, and we can see that 2 mm are too much. Because this is a parametric system, we can simply double-click the face and change the offset to 1 mm. This is very obvious for any CAD user, but it's very rare in 3D printing preparation software because they are all based on mesh and cannot support parametric features. The next stage is setting the part orientation. The first thing we see when we open the positioning tool is a list of attributes pertaining to the current orientation of the part. And we can see it updated as we change the orientation. We can also see a set of colors. Let's see what they mean. Blue means up-facing areas, yellow means down-facing area, and red means overhang area, which means areas that require supports. In pink, we have staircase areas, which we don't see in this orientation, but if we change the staircase threshold angle, we will be able to see it. We'll now run the auto orientation, which helps us find the best orientation according to different criteria, such as time, tray area, supports, internal supports, and approximated stress. For each criteria, we get a block which represents its orientation and shows us bars indicating its rating on all criteria. For example, the approximated stress optimal orientation shows very low rating for internal supports, as it will require many supports on the internal tubes. If we manually rotate the part, we get an additional block showing us ratings for each criterion. The best fit gives us an optimal orientation based on different weights for each criterion. In this case, we want to give the maximal weight for the internal supports so that we don't require supports on the internal tubes. Next up is support generation. We'll start off by creating support regions. The automatic analysis creates supports regions of different types: regular supports, lowest areas, and lowest points. Having exact CAD data, solids and surfaces, allows us to get smooth regions without jagged edges. We'll start by creating the most common support, a wall support. As you can see, a single wall doesn't really support much. We will need to replace the region with a pattern of curves covering the entire region. We can create different types of patterns. For example, an offset pattern, which is a conformal pattern, to which we can add web lines. We can also create a hedge pattern. We can use different edges, and you can also define your own hedge pattern. We can also add fragmentation, which helps with removal of the supports in post-processing. We can better visualize this by looking at the lines of the fragmentation. As we can see, they are not really suited to a honeycomb pattern. For that, we can use the cell-based fragmentation, which is dedicated to a grid or a honeycomb fragmentation, and we can also add fragmentation to the outer boundaries. We can now create a wall support on the pattern we created on the region. On the wall support dialog, there are many parameters you can control. For example, the shape of the perforations. For each parameter on the dialog, there is a picture that explains what it does. There are also additional parameters in the advanced pane, but normally you will not need to use these parameters, as you can use predefined templates, which we will touch on later. The preview of the support shows us some red walls. These walls are marked because they are touching the part. Sometimes this is desired when we create gussets, but in this case we want to avoid it, and we can use different tilting methods to keep the supports away from the part. We will now create a similar support on another region. We have just created the support manually, but normally we can use predefined templates provided with the system. We can also save manually created support as templates, or we can use an existing support as a reference template for a new support. Any support that is created from a template, either predefined or a reference template, can be fully edited just the same as a manually created support. In fact, we can create a full set of supports for a part using the meta templates. A meta template is a collection of templates assigned to different regions according to their different attributes. This may include the region area, the Z level of the region, ease of removal of the region, the angle of the region, and many other parameters. You may use a meta template with a set of rules provided with the system, or define your own rules based on your knowledge. As with any support created by a template, supports created by the meta templates can also be edited. We can easily spend another 30 minutes or an hour discussing the different support options of 3D Expert, but we are very short in time, so we will create one manual cone support and move on to the next stage. We are moving on to structure optimization, namely lattice, infill, and texture creation. Lattices are made of a geometrical cell repeated in X, Y, and Z. After we select the volume that will hold the lattice, we can control the cell type that will be used and the X, Y, and Z size of the cell. We can also control the thickness of nodes and connectors. 3D Expert is unique in providing immediate preview of the 3D lattice and allowing editing with immediate feedback. We can also use stochastic cells and control their randomization. This is usually used for medical purposes to enhance bone growth into an implant. We can also use the shaped cell, which can take on any shape, B-rep or mesh, and repeat it as a lattice cell. All lattice parameters can be saved into a template and then be reused. We can define an outer face for a lattice, and the system will provide smooth connections to avoid injury. There are also very efficient function-based lattices such as gyroid, Schwarz-P, and Schwarz-D. Volume lattices are very useful for weight reduction and can also be used for medical purposes as we see here. Next, we will look at a surface lattice. A surface lattice can be attached to a solid face or a mesh area. There are several types of surface lattices, and for each we can control the size of the cells, the thickness of the elements, and their shape. We are starting with two types of sprout lattices, and then move on to tetrahedron and truncated tetrahedron. On those lattices, we can add a number of layers, one on top of the other. The same goes for the connected quads and the solidified lattice. Surface lattices are often used to improve the connection between an implant and an organic tissue, or to add a rough texture to an external surface of the part. Let's go back to the part we started with. A lattice can be used here to lightweight the part. We have a few lattice templates saved here that we can use. And as we saw in support, a lattice created from a template can be edited by the user. Once we have settled on a template that we like, we would now want to add a shell to the lattice because we don't want the lattice to fill out the entire volume. We define a thick shell of 6 millimeters. Since we don't want the powder to be trapped inside the part, we can define an open face or drain holes in the part. The lattice on the open face will get smooth connections, as we saw on the previous part. I have just now realized that the 3 holes on the clamping surface would actually be drilled, so they should be removed for the purpose of 3D printing. Since we are working in a history-based parametric system, we can simply go up the feature tree before the existence of the lattice, remove these holes, and then reapply the lattice. The lattice then takes up the volume of the removed holes. Again, as with supports, we could spend a lot of time talking about the multitude of functionality 3D Expert offers when it comes to structure optimization. But since we don't have a lot of time, we will quickly look at 2 items. The first is lattice FEA and lattice optimization. 3D Expert offers an FEA-based stress-strain analysis for parts and their lattices. We can see the stress formed on the part and the deviation caused by the pressure applied. The system can work with multiple load cases, including different types of pressure and frequency analysis for vibrations. With this analysis data, we go to the lattice optimization. There, the system can make nodes and connector thinner where there is less stress and thicker where there is more stress. This can give us a part that is as strong at lower weight or much stronger with minimal weight addition. The optimization is iterative, and we can see changes in mass, stress, and deviation for each iteration. The second item is texturing. We can see here a brace for scoliosis with very detailed texture work. We can add any picture at any size and angle at any position on any surface as a single picture or as tiles and use them to form protrusions or depressions on the surface. Our next topic is build simulation. This simulation is powered by Amphion from Additive Works. It is fully integrated within 3D Expert. This simulation takes into account material properties and sintering processes to show us what happens to the part while it is printed layer after layer. In this case, we are looking at displacement, the deviation formed by stresses and cooling of the metal. We will start at the bottom layer and start moving up one layer at a time We can see the maximal deviation at each layer. As we move up, we can see this value changing, and we can look at different sections of the model. We can also look at stress, plasticity, which will show us where material may fail. We can also look at displacement from a perspective of inner and outer, meaning where the material goes in and where the material goes out of its original location. We can also look at recorder interference. This will tell us where material goes up as it cools down and may hurt the recorder. We can see the model with or without supports. And keep pushing up through the layers until we reach the top of the part. If we look at stress, this is the stress map when printing is completed. We can then look at what happens to the part after heat treatment. We can see the stress is reduced dramatically. The system can also simulate what happens to the part after plate cut, after we remove the part from the plate. And we can also look at what happens after we remove the supports from the part. We can also ask the system to generate a compensated model, which is the model that should be printed taking into account all displacements in order to receive in the end the original dimensions of the part. Build simulation is very useful to verify that the part will be printed successfully, that our orientation is correct, and that the supports we used and created are the right ones. It can help us save time and money by reducing iterations and failed builds, and even preventing damage to equipment through the recorder interference analysis. We will now start talking about labeling. We will get back to this after we look at tray arrangement. 3D Expert offers smart labeling. This means we can put in a symbolic label and then replace it with the appropriate label for that specific printed part later on. Right now we are putting in the amount of characters that will be required in the final label. We can create the label as engraved or protruding or as sunken protrusion, which means we have a small sunken rectangle and the label is protruding inside it. Please ignore this small meshing artifact. We can also create a detachable label, which is useful for small parts or cases where we don't want the label to stay on the part. We can control the size of the detachable label, its distance from the part, its angle, and so on. In this case, we chose to create the text as actual geometry, but we can create it as symbolic text as we did with the label. As I said, we will get back to smart labeling and see what we can do with this symbolic text when we deal with tray arrangement. Now let's talk about slicing. For the purpose of slicing, the system attaches what we call technology or build parameters to each object in the system. The attachment is done automatically by the system based on the type of the object, for example, wall support, cone support, lattice part, etc. But the user can manually intervene and select a different technology for each object. When we open the slicing tool, we can see how many objects we have of each type and can begin the slicing. It is important to know that the build parameters are provided for each material with the system. However, for customers who are willing and have the capacity to define their own parameters, 3D Expert offers an unprecedented open interface to control each and every parameter of the slicing and the hedging. There is much to be told about build parameters, but unfortunately, we don't have time to go into it. Two other issues I would like to touch on quickly are 3D zoning and offloading calculation. 3D zoning is a patent-pending technology included with 3D Expert. It allows you to create virtual 3D volumes and assign specific build parameters to it without splitting the part. This allows you to define special build parameters for thin area, concentric slicing, and rough slicing without forming a weak point in the part. Offloading calculation allows you to add slicing machines in a private cloud to which you can offload the slicing and enhance slicing speed dramatically. If you want to hear more about any of these topics, please contact us after the webinar. Naturally, we do not have time to wait for the slicing to be completed, so we will switch to a pre-sliced file. With the slice viewer, we can look at each one of the slices and review the scan path on that slice. We can see it with the part underneath the slices or see the scan path alone. If we take a closer look, we can see the lattice and support scan path appear every other layer. That's because they have a build parameter that defines that they will be sliced every 60 microns, while the part itself is sliced every 30 microns. We can also see different regions of the scan path alternating using a smart bricking method that makes sure we do not repeat the same scan path in the same area. If we have defined special printing conditions or parameters for down-facing areas, curves that are recognized as inside the down-facing area will be marked red. Curves that are inside an up-facing area will be marked green. In this case, we have been working with a multi-laser printer, and we can also see which area of the scan path was created by which printing head. We are nearing the end of the process. Let's talk about tray arrangement. Right now we are focusing on nesting in 2D of a single part. We start the nesting calculation and the system will iteratively try to fit more and more parts into the tray. In this case we have asked not to rotate the part so as not to interfere with the gas flow. Finally 10 parts could fit inside the tray. Note that only one part here is really sliced and the other parts are instances of the same part, so we do not have to reslice them. Now it is time to go back to smart labeling. We can see the labels of all the instances of the part we brought in. And we can export them to Excel and then assign a different number to each one of the instances. The data can then be read back into the label manager and we can see that each instance got a different number. If we look at the parts themselves, we can see those numbers on the labels. The text is still virtual. We can now reopen the label manager and turn it into actual geometry. The last part of the process is to do incremental slicing for the labeling only. The rest of the part keeps its existing slicing and the scan path of the labels is merged into it. 3D Expert has additional tray arrangement tools. Some are more applicable for plastic printing. For example, Joint Cut, which allows you to divide a part that is too large to fit into the tray. We also have 3D nesting and different copying tools for both 2D and 3D. The last printing operation is sending the part to the printer. The Send to Print tool allows us to output the scan path in the machine format, and we can also choose to export mesh files with different formats. Geometry can be exported as supports only or non-supports objects, or divide the supports and non-supports to different files. We can also choose if we want to export lattice, which is quite a heavy export, and what kind of unification operations we want to do on that lattice. Finally, we have the post-processing operations. 3D Expert has all the tools required to program any post-processing operation, including milling, drilling, tapping, etc. Thank you for watching this short 3D Expert demo. As we said, we got a chance to take a quick look at each step of the process and see the tools 3D Expert offers for that stage. There is much more functionality and capabilities offered by the software, and we will be happy to show them and discuss them with you.
Thank you very much, Moz. To sum it all up, let's review the key takeaway from this webinar before we move to the question and answer part. So first, what we saw that it takes more than a 3D model and a good printer to get quality prints. We saw that there is an inherent gap between a 3D CAD model and a ready-to-print model. The missing link to bridge this gap is the additive manufacturing software, which we sometimes call the 3D X factor, a key element that doesn't always get the attention it deserves. We saw that additive manufacturing software is critical not only to achieve successful prints, but also for the profitability of a 3D printing business. We then reviewed the different approaches for additive manufacturing software and understood the differences between them. And finally, we were able to see our 3D Expert additive manufacturing software in action. And this is, of course, a good opportunity to mention that it was only a sneak peek into the software capabilities, and you are welcome to contact us for a more thorough demonstration. With that, I would like to thank you all for your time, and I open the stage for any questions that you may have. Please use the questions tab to type in your questions. We'll